What I will try to do is I'll try to introduce how deep learning works, how machine learning works, what is AI, what is deep learning, describe some of these terms, describe how they interact with each other, and give you a brief intro of why deep learning is so relevant in today's environment. So this is how we'll run this session. We'll have, so I'll first describe these terms. I'll describe how deep learning is different from machine learning and AI. I'll talk about why is deep learning better than traditional methods. So in all of this, I'll focus on computer vision as an example. So computer vision is the image recognition, basically, looking at images and understanding images. But the same applies for other fields. For example, Lee has done a lot of work in speech recognition or NLP and so on. But I will pick up computer vision as the example here. I'll go through a brief deep learning 101, sort of in 5 minutes, try to describe how it works, how the algorithm works. And I'll talk about what's changed now and what's the future, right? So typically, I mean, traditionally, if you look at AI, right, if you want to think about a machine which is artificially intelligent, it has to have these features. It has to be able to communicate successfully, and typically in English, so it has to be able to communicate with human beings. It has to represent knowledge, so it has to store whatever it hears or reads or sees. Right? It has to have automated reasoning to use the stored information to answer questions and draw conclusions or basically answer questions. Machine learning to adapt to new circumstances and to detect or extrapolate patterns. Computer vision to perceive and see objects. And robotics to manipulate and move about. So if a machine has all of these features, all of these aspects, it can be called an artificially intelligent machine, right? So machine learning is basically one field of AI. And within machine learning, we think about machine learning as of three types, right? Supervised learning, unsupervised learning, and reinforcement learning. I'll talk a little bit more about, I have some more slides on these, I'll talk about this more. But typically, I mean, when you think about supervised learning, a lot of these traditional machine learning methods are support vector machines, decision trees, random forest, logistic and linear regression. Unsupervised learning would be something like clustering, principal component analysis, singular value decomposition, non-negative matrix factorization. And reinforcement learning, Lee spoke about, I'll speak about a little bit as well. And currently, I mean, if you think about what is deep learning is actually across all of these. So deep learning can do supervised, unsupervised, reinforcement. And deep learning and artificial neural networks are sort of synonymous. So basically, these are neural networks modeled, artificial neural networks modeled on the human brain. And they can learn somewhat like humans do in some ways. And deep learning is basically just a synonym for, just means that you're building deeper networks. So Lee spoke about an example with image recognition where it had 150 layers. So basically, the more layers you can get, the better accuracy you're getting. Today, that's what we are seeing in this field. So coming to supervised learning, it's simple. I mean, so here, again, the objective is to recognize handwritten digits. So there is 4, 8, 2, 5, 3, and 7. These are handwritten digits. And supervision is basically we are providing an input saying that it's a 4, this is a 4, this is an 8, this is a 2, this is a 5. And with that input, now the machine can learn. Now, of course, this is expensive because if you have to label thousands of images or millions of images, it takes a lot of work to do that. And especially the kind of work we do in healthcare, it's difficult to get that done. So that's where unsupervised plays a part. So can we figure out some patterns here? So looking at this, can you figure out any patterns here? Are there specific objects you can see there? Okay, so you can see two patterns, right? So can everybody see two patterns there? So our human brains can see basically two patterns in that, right? Now what I have written here are basically the digit 5 and the digit 7 in Hindi numerals. So if you look at the Hindi alphabet, that's 5 and 7. So this is 7 and that's 5. And so going back, I mean, you can basically, we can figure out that there are two. I mean, even without supervision, without actually telling that this is a 5 or a 7, human brain can figure out that these are two different digits. So that's basically unsupervised learning. Now, we have to train the machines to also figure out that, yeah, these are two different things. And clustering is one way to do that. There are other methods. But the idea is how do you, without supervision, train a machine to understand different patterns in the data? Then reinforcement learning, Lee spoke about it a little bit. The idea here is that, I mean, I'll play one of these just to show, right? So this is basically the ball, this particular bat hitting the ball, right? Now, in a traditional method, if you do not use deep learning, traditionally what you would do is you would actually look at that paddle, and look at where the ball is, and try to move the paddle so that it can sort of understand the physics of the movement of the ball, and try to move the paddle so it can hit the ball. That's what you would traditionally do with traditional methods. With deep learning, what you're doing is actually you're able to give these images. So in this case, all of these are examples where the images have been given to the machine. There is no rules given, no knowledge of physics, no knowledge of where the ball is or what the ball is doing. It's just learning from the image itself what the ball is, where the ball is, and it's learning to hit the ball, right? And the other part of reinforcement learning is that it's sort of learning in the Pavlovian manner from experience. So every time, I mean, you take an action, it gets a feedback, right? So it takes so there is think about an environment where there is uncertainty. So it doesn't know what action to take. And so it takes an action, figures out a feedback, gets a reward for that action, and it looks at the future. I mean, so finally it's looking at in long-term future, what is the best action it can take? What is the action it can take so that in the long-term future, it can maximize its reward. So that's basically what reinforcement learning is doing. Talk about why is deep learning better than traditional methods, right? So think about this image here. So when we see this image, we see that there are basically two electric kettles. There is a toaster, there is a coffee mug, there is a sink, and so on, right? What the camera sees is basically a bunch of numbers. These are pixel values. The pixel values go from 0 to 255, right? So 0 is white and 255 is black. And traditionally, I mean, so without deep learning, with traditional techniques, what you would do is you would take the image, you would use features like shift features, these features, there are types of features. A feature is basically, and shape context. Feature is basically looking at this and saying that, okay, if the cup, there is a handle of the cup, that's a shape, you define a certain shape. And then you say that, okay, if you find that shape, you know that it's a cup, right? So you can do that for different objects, but finally it's using our intelligence, it's using intelligence of a data scientist to figure out what features are relevant for a certain problem, and then use those features to classify between objects, let's say identify objects or classify between whether it's a cup or not a cup, right? So it's using the intelligence of the data scientist there, whereas with deep learning, that's going away. So what deep learning is doing is that when you look at, it's basically these are different layers of the network. This is the input, it's taking the input here, and the last layer is the output layer, which is basically producing an output. And think of the output as between, let's say, whether this object is of a cup, whether this image is of a cup or not a cup, right? And the input is basically, in this case, now with deep learning, what we're doing is we're actually giving raw pixel data as input. So it's just taking the pixel values, the 0 to 255 values as input, and without any feature engineering, so it gets rid of feature engineering. We don't have to think about what features to create for this particular problem. So it can basically be taken for all kinds of images. So we don't have to identify features to, like, for example, think about features to identify a bottle or a Coke bottle or a coffee mug or anything else, right? So it can do all of that in one go. And so when you think about it, the edges are basically, I mean, you're taking raw pixels and you're learning hierarchically more advanced image features. So basically, first level, you might learn some edges. Then you might, if you're thinking about a face, you might learn something like human eyes or nose or ears and so on. And the last might be object models. So this is trained on ImageNet data, which is basically what we spoke about. It's a large 1.2 million database of images of different kinds of objects, including animals. And this image is basically, it's creating a probability of this image being of different classes. So it can have 1,000 classes, and it's basically saying that it's a high 0.93 probability is of it being a jaguar, right? Now, what you see on the top are different layers of this, of the network, of the neural network that was used to do this prediction. And what I'll show you is as you go through these layers, actually, let me, scroll to the left side so that you can see. As I go through these layers are learning, so this is the first layer, right? So as I said, I mean, the first layer is learning some edges. So you can see that it's learning edges, different types of edges. So it's basically this different types of edges here. This goes this direction, the other one goes the other slanting direction. And it learns some color features also, right? Some numbers, somewhere it learns some numbers. And so the first layer is learning something basic, right? Now if you go to the second layer, this is the second layer here, that learns a little bit more advanced features. You can see that it's not learning the edge part, it learns circles, for example, or it learns some certain types of features which might occur in fabrics. These are basically parts which might occur in different kinds of objects. And as you go further, I mean, so you basically, this is, for example, microphones, right? You can see that it's recognizing that. And this looks like buttons and tires, I mean, those circular kinds of objects. And till you, in the end, I mean, it's basically figuring out different, each of these are neurons which get fired, the last ones. And these are basically fired, these are not fired, so all of the black ones are not fired for this particular image of a jaguar. whereas this one is, and this will correspond to lots of images of jaguars, basically. But if you look at the other neurons which are not fired, they belong to other classes. For example, this belongs to dogs, or this belongs to, again, dogs, and this is Band-Aids. So each neuron is basically fired based upon certain types of input data. So now I wanted to spend 5 minutes going through a brief review of how these algorithms work. So think about, the problem we'll take is we have got these digits 2 and 3, handwritten digits, right? So it's basically 2 and lots of 2 and 3, and we have got 50,000 examples of these. And they are all been labeled, so this is a supervised learning problem. The labels are, again, it says either 2 or a 3, right? Now, I've written it as output is probability. So it says that if it is a 2, then the probability of being a 2 is 1, and probability of being a 3 is 0. So we say it's 1, 0. And if it's a 3, the probability of being a 2 is 0, and probability of being a 3 is 1, and so it's 0, 1. So that's the output. And we have labels for, so basically we have labels for all of these images. And what we do is then, for the first layer, basically the P1 to P784, that's the input layer, right? And so these images, all of these images are 28 by 28 pixels. So there are 28 by 28 pixels, that is 784 pixels total. And each of those pixels goes in as an input to this network. And what is the H1 to H100 are basically what's called hidden layers. They are basically learning some features of the data, like I showed in the other example of the Jaguar. They are learning some features of the data. And the last one, the P2 and P3 are basically the probability of being a 2 or a probability of being a 3. Those are the output layers. Right? So what do we do? We basically, so just before that, this is basically how the digit 2 would look like. So if you think about it, lots of zeros. And if you can see, there's a slide 2 that you can see there, which are basically the pixel values. So 207, 252, these are, these large numbers are basically the areas where the handwritten area is present. So how do you start with this? You start with initializing this network with random weights. Right? So you say that, basically the idea is I want to create a set of weights which can basically take this P1 to P784 and map that to the probability of being a 2 and a 3. Right? So I will initialize with random weights. In this case, the number of weights is 784 is the number of input neurons. And then there is 100, second layer is 100. So that's 78,400 weights here. The second layer would have, second set of weights would have basically 100 times 2, which is 200. So 78,600 weights are there. And what we do then is we present one training example. So we take the first example and we pass it through the network. Right? So we feed it through the network and we basically put all the pixel values in the first layer, and then we feed it through with the weights, and it gives us a probability of 0.6 and 0.4. The probability of being a 2 is 0.6, probability of being 3 is 0.4. Right? Now we know that that's not true. So we know that this particular example is a 2, so the probability should have been 1 and 0. So we calculate the error. One way of calculating error is just 1 minus 0.6 whole square plus 0 minus 0.4 whole square, which is mean square error, and that error comes to 0.32. Right? So now we know that we have a set of weights which is not optimal because it's not exactly producing the output that we wanted, and there is an error there. Idea is how do we propagate that error backward, which is called a back propagation algorithm, which is the foundation of all of these. Is basically we propagate that error backward, adjust all the weights, so that it can be better at predicting that 1-0 output. Right? So we do that, and then we continue to the next example. So take the next example, again adjust the weights, and repeat this for each training example, taking one random training instance and making slight weight adjustment at each time. And then we have a, let's say, once we have trained across all the 50,000 images, now we can start testing it. So basically this is the same technology which is used in check processing, the image recognition, check processing, number recognition. And so we can take a testing example of 2, right? And this is the example, and you can say that the probability is 0.9 and 0.1, which says that it's a 2. And you can set a threshold value saying that, okay, if the probability is greater than 0.7, I know that it's a 2. So that's basically how these algorithms work. And of course, there are lots of other techniques which allows us to become deeper and deeper. But this is the basic way of how deep learning, how neural networks work, and how deep learning works. I also wanted to briefly talk about what's changed now. So one of the things which has happened, with Google and Facebook and all of these companies, is that there's a lot more data now. There's so much, exponentially higher data than what was available earlier. Right? So over the last 3-4 years, we have seen a lot of progress in deep learning, and that's because one of the reasons is more data. Second is more computing power. So, I mean, a lot of you must have heard about Google doing this cat videos. So you might have seen those cat videos, which is done by Andrew Ng from Google. This was in 2012. In 2012, he did this. He ran this on 12,000. So I mean, obviously Google, so they have a lot of computing power. They ran it on 12,000 CPUs, 16,000 CPUs, not 12,000, 16,000 CPUs. And that's a large number. I mean, it's fairly large. But the thing is that for these kinds of processing, you need parallel processing power. You don't need sequential processing capability. A CPU is typically very good for a lot of sequential processing, but not good for parallel processing. And the state, I mean, the kind of GPUs that we use, which are $1,200 a piece, I mean, those have today, I mean, they have 3,600 cores. If you have 4 of them, you can actually beat what Google was doing in 2012. So you can actually easily, I mean, it's basically allowing us to run this algorithm much, much faster than we could earlier. And because of both more data and more computing power, we are actually able to now experiment faster. And a lot of research has happened. I mean, Lee and Jeff Hinton worked on making this. I mean, so Lee actually worked on making the first industrial application of deep learning, which was in speech recognition in 2009. And a lot of research, I mean, one of the ideas, for example, is, so this is, is something called dropout. You know, to talk about that, I'll just go back to the previous example. What can happen is that these weights can be tuned for one specific type of instance. So for example, you could learn to recognize all of these digits, not being able to generalize to any new digit that comes up. It could learn exact features, exactly how this 2 looks, and not be able to identify a 2 which looks slightly different. So one way to fix that was, I mean, which is a fairly obvious approach, is to sort of say that, okay, the hidden layer, that H1 to H100, I will train, each time I pass an example, I will not have all of those in the network. I'll just take 50. So randomly I'll select 50 and I'll do the forward pass and keep on doing that. So when you actually take 50 at a time, each of those neurons cannot learn anything specific about an image. So they all become fairly smart at generalizing across images. So that's one of the approaches. There are lots of other things, newer types of weight initialization, activation layers. I mean, lots of approaches have come about in the last few years in this space. And the last thing which I wanted to speak about was why, I mean, what is the future, right? So if you see this picture, you can recognize that it's a funny picture. And it's funny because of various different things. But for a machine to understand, it's a tough task. And to think about it, there is, first of all, I mean, this person is standing on a weighing machine. So it has to figure out that it's a weighing machine and a person is standing on that. There are these 5 or 6 people in this image, right? It also has to figure out that there are these 2 mirrors. And so the President Obama on this mirror is the same as the President Obama standing there. So it has to figure that out. It has to also be able to identify that a person's weight is something that they're conscious about. So if this person's weight is showing higher because of President Obama stepping on the weighing machine, it's actually a funny thing. And it's basically, I mean, it's also funny because it's President Obama. So there is also that attribution that it's a president doing this thing. So there's a lot of level of detail involved. And today, I mean, machines are able to recognize images very well. In fact, understanding and categorizing images, they are doing better than human beings. I mean, we are at 2.5% error in terms of identifying images, which is human error was around 5% on a challenge called ImageNet challenge. But I think there is a lot in terms of learning from the images and contextualizing it and creating meaning out of it. So that's where deep learning is headed in the future.